Hi everyone, in this tutorial we are going to learn how to use particle or Popnet knowledge inside fluid simulations. We are going to see how easy it is to apply particle force that we already explored in other tutorials into fluid simulation and mix fluids with different parameters like viscosity and density. Okay, let's start by placing a box. Okay, and let's dive in. Let's start with a simple box, 10 by 0.1 and 10, something like this. Cool. So this is our base for our fluid simulation. Now we can do two things. We can go up, select our node and go to the shelf tool and click flip fluid from object. But let's do the other way. We have our box. Let's place a DOP network. And we are going to create our fluid simulation inside this DOPnet. Okay, so let's dive in. We have only one output. Let's start by placing a flip solver because we want to create a fluid simulation. We need a flip object, right? And let's wire this into the first input of flip solver, and we want a gravity force. Okay, so we have a really basic system. Let's configure this flip object. We have a default fluid. You see that little box. First, let's change our guides. I think it's on guides, particles, instead of sprites, let's use particles. Okay, we have that there. Let's go to initial data. On subpath we have a default fluid. Let's replace with our box. Let me do one thing before. Let's place a null because we are going to change after a while we are going to change this. So let's place a null and let's place out base fluids. Okay, so inside our DOPnet let's wire that null. Okay, so now we have our particles. I'm going to increase the size of those particles. You press D to have your display options, and here on geometry particles let's increase the size to 6. Okay, so now we can see the particles a little bit better. Okay, so now we have this container with the fluid inside. Let's change that container. Let's go to the flip solver, volume motion, and on volume limits let's decrease this to 10, maybe 10 by 10. And I want this container on the floor. So I'm going to right click on the Y here, right click, copy parameter, and here let's place relative reference and divide by 2. So it will always stay. I have an error here. Okay, so our container will be always at the floor. If we decrease this size, it will be always on the floor. Okay, other thing I want to do is close boundaries. And if we press play, you'll see our particle simulation. Pretty simple, right? This is how you create your basic flip solver. And let's do some things. You see some particles are getting born right here. See, because we have some receive on our particle motions. I like to render and if you want to render it like that, I like to render the flip solvers with particles to get that effect like sand. But for that, I need to do a few things. On particle motion, on behavior, I don't want to kill outside volume limits. Add ID attribute, and I don't want to reseed particles. So when we start, we have these particles, and we are not getting more particles because of the space. Okay, so we have this. If you want more resolutions on the particles, you can go to flip object and decrease this particle separation. I'm going to decrease to 0.05. As you see, now we have more resolution on the flip simulation. But because I'm recording this tutorial, I'm going to crank this up a little bit to 75. Let me see if my computer can handle everything. I think so. Okay, so we have our flip simulation, basic one, right? So now how can we apply the particle knowledge we already have that I gave on different tutorials to this flip simulation? Because sometimes it's hard, and some patrons were asking how we can apply that knowledge to our flip simulation so we have more fluid organic animations. And if you see here these inputs, on the last one you may already know this one. If you want to emit particles, you link a source volume to this one, so you will emit fluids, right? On this volume velocity, we saw it already, you can link volumes to here, like advect particles to advect particles. And on the second one, as you can see, it says particle velocity. On this second input, we can link our particles nodes here. For example, let's place a pop force. Pop force. Okay, normally we use this on Popnet, right? But if you link this to the particle velocity, let's increase this amplitude. Okay. You'll see this pop force will change our flip simulation. And this is simple as that. With this second input, you can link anything you do on Popnet here. Okay? Pretty cool, right? And because you are using a flip solver, your animation will be more organic. So let's try something like I did on the, I think it was on second or third tutorial. Let's place a pop VOP, and let's wire this to the particle velocity. Let's play with this pop VOP. I'm going to do the same I did on, I think, second or third tutorial. I'm going to use an image. Let me check if I have that one here. Sorry. Okay. Let's start with this one. We are going to use this image, and on the white pixels we are going to add some force, and on the black they will stay at, they have no force on themselves. Okay, so to do that, you remember you need to place a color map. Let's pick that one I want. Where is it? Why can't I go? Sorry. I don't remember the name. It's Ricardo Gomez. Okay. So we have our color map. We need to fit the position. Position is a vector, remember, and we need to give a float to U and to the vertical V. Okay. You remember we can convert vector to float, use the X to the U, to the horizontal, and in our case we are going to use the Z because our fluids are on the ground, right? On Z and X and Z plane. So if I wire this into the color and press play, you'll see something is happening here. Let me zoom out so you can see it clear better. Something is happening here. It took me a while to figure this out. It's just stupid, but when you have white color, air particles will have the guide visualization, the blue one. Okay, so don't be scared with that. It's working, but our image is not really good, right? Because we need to do one thing before. Remember, we need to fit this size, because the color map works from 0 to 1, I think, and we have our particle from -5 to 5, right? I think I have my... Okay, let's see like this, -5 to 5, and Z, it's the same. So remember, we need to do a fit range here, and our source mean is from -5, Y I don't care, -5 to 5, Y we don't care, and oops, I did something wrong. This is -5 and 5. Okay, and okay, I'm doing this wrong. Oh no, sorry. This is source mean. I was getting this all wrong. And source max is from -5 to 5. Okay. Cool. So I hope you can see the image here. Right? Same image. It's flipped, so don't be afraid of that. We don't care. It's not important for this tutorial to fix the image. We just want to use now our white pixels will have some force, right? So let's do something with that. So we have our color. You know our color is from 0 to 1. So these white particles have a vector of 1, right? That's why it's getting that pixel. So let's add some vector. Let's place a vector. Can I do vector? If I do constant, let's see. Add a constant, but I won't add a vector. Let me see here. Nah. Let's do this the other way around. Constant, add a constant. I want a vector. Okay. And I want like 5. Right now, if I add this to force or velocity, maybe 5 is way too low. Cool. So our fluids now are going up, right? Because we are adding every frame a force of 50 on Y. Let's go call it up force. Okay, but right now everything is chaotic, right? So let's use our color map to multiply this force, so we will have only force on the white pixels. Sorry. So let's multiply. Remember we did this on the first tutorial. Let's multiply. Let me do this in order. We're going to multiply the force we want by the color, and then apply this. So now, as you see, let's go to the first frame so it's easy to see. Now, as you see, we are only applying that force to the white pixels. I hope you can see. Let me increase this. Let's see if this helps a little bit. Okay, I hope this is way better. So as you see, now we are applying this force depending the color map. Let's change the color map. Let me check. Let's try and use this one, geometric. It's more clean. So let's go to geometric background. Let's simulate again. Boom. See, pretty cool. But right now, we are applying every frame this force, right? And we want this to get down. Let me decrease this a little bit. Let's go 150, only 5 seconds. I wanted some time to turn off the force, right? And I had a few problems here. And this is a really nice tip, because I figured out, and I read on some forums, that PopVop, the VOP nodes, works different from the DOP and solver nodes. Okay, let me show you what I'm saying. Imagine at frame 30 we want to turn off our force. Okay, so after frame 31 we don't have more force on these particles, so they will go down, right? Let's see what it's going to do. I'm going to decrease or increase the particle separation, decrease the resolution, see it more faster. Okay, let's go. And if you see, as you can see, our particles are still getting the same velocity, same force, sorry, even after we turn off the force on that constant vector, right? Why is that? Because outside the PopVop, or let me explain only the PopVop because it's really to understand. Inside the PopVop, it is calculating everything that is happening here, each frame. For example, on frame 2, it's going to check the frame 1. On frame 3, it's going to check the frame before. Here, when we turn off, it's not checking this value. It's checking the value on the frame before. So on frame 31, we have a force of 50, right? So it's going to stay on 50. On frame 32, it's going to check on what is happening on frame 31, and we still have the force on 50, right? So it's going to keep adding 50 to the force every single frame. Okay, so how do we turn this off, right? We don't want to turn off the PopVop because we want to still imagine if you had a curl noise here. You want to keep adding that curl noise and not turn off. So the way to do that, to turn off our constant vector here, the only way to do that, and the simple way, is to add a pop wrangle outside, wire this into the PopVop, and let's create a parameter, right? So we have a up force vector, right? That is, let's set 0, 50, 0, right? Or we can just add a float, sorry, up force, and let's create a channel for this, up force. I did a mistake there, let me fix this, Hupo force. So we have this new parameter, up force, that is a float, simple as that. And if we press this little button, now we have the slide. Let's increase this to 50. Okay. And we have this, I'm going to copy this up force. How we can use that here? Remember that bind export. Now we can bind import that parameter, same parameter, up force, right? So we can use any parameter we have on our particles. And now use that one. Let's convert float to vector. Wire this in to the y value and then multiply. If you see, now we are still getting the same, but now we are controlling the force, the up force, outside the PopVop. So that means that now on frame 10, for example, I'm going to turn off our force, and you'll see that our particles will go up, and then after frame 11 they will start going down because they don't have more up force. Okay, let's check that out. Pretty cool, right? Okay, I think I create this way too early. Let's go to frame 60, no, 30. 30 was a good one. Let's dial this down a little bit. And let's go to 31, no, not 31, let's go to 60. And let's turn this down. So as you can see, this is a little trick to control parameters and animate parameters inside a pop-up. Even if you are inside a Popnet or any other node that you have a pop-up, if you want to animate anything inside, you just need to create a wrangle and create a channel for that and animate outside the pop-up and then wire that in. Simple as that. So you can see our particles are going up, and after a while we are decreasing the force, so they will go down. Pretty cool, right? Other thing you can do is play with this thing. For example, you have a color map. You can add different density and viscosity to each particle. So for example, if you have a color image, let me check this one, for example. Imagine this image. On the blue ink, for example, we can add like 25 viscosity, and on the pink particles we can add a different viscosity. How we can do that? Let's go back. Let me show you a simple thing. Here on particle volume, I think it's on volume, yeah, volume motion, you have viscosity and density. Everything here you can adjust as you want, right? For example, on viscosity, to have different viscosity to each particle, to have different fluids on the same simulation, you can enable viscosity and viscosity by attribute. Now, if you add this viscosity to your particles as a parameter, like we did on pop wrangle, for example, if you add a simple viscosity, if you write that correctly, if you have this, for example, if you add a parameter float called viscosity, now your particles will have that value for viscosity, ignoring this one. Where is physical? Okay, that value will overwrite this one. Okay, same goes for density. Density by attribute. If you go here, sorry, and have density, now your particles will have a density of 300. Okay. Because they are more dense and more viscosity, they don't go up like they used to do. But we don't want this simple thing. We don't want the viscosity, the same viscosity for every particle. For that, we could just go here and add this value here, right? So let's change this thing for a bit. Okay, so we have a color map. I'm going back and let's play with our particles before we jump into the DOP network. Okay, I'm going to show you a different way to create your DOPnet. Okay, so let's start by placing a point volume. How do you write that? Yeah, points from volume. This is kind of like the scatter node. Okay. And let's jitter scale, let's increase it to 1. Okay, cool. Okay, simple. So we scatter some points and let's color them, right? Remember that attribute from map. This way we can color our image. I'm going to increase or increase the resolution, as I said, decrease the particle separation, right? On this node, it's simple to have this the right way. Okay, just invert U or invert vertical if you want this way. This way is the right one. You have minus here, positive, minus Z, and positive Z. Okay, let's change the color. Okay, pretty cool. So now let's add that attributes, remember? Those ones, the viscosity and the density, to our particles outside the dot network. Okay, let's put a wrangle, and we are going to use a simple vex code to do that. Okay, don't be afraid. So let's start our vex code. Let's Alt E to have our window. We are going to use a simple statement to check the color of our particles, right? We are going to check the channel blue, and let's check if this is 0.5, for example. If this is true, we are going to add a simple viscosity. Sorry, I can't write today. Viscosity, some random value, and then density. If it is blue, it's going to have higher density, and we are going to use is blue just to work as a Boolean value. We don't have Booleans here on Vex, so else, and here we are going to have different values, right? So we don't want viscosity for the pink one, we want the density as water, and it's not blue. Okay, so we have this. And how do we know, if we go to geometry spreadsheet, how do we know that we are going to apply viscosity for where is viscosity? How do we know this particle is a blue one? Let's do a little trick. Let's group by expression. Okay, group 1, and then let's blast. I don't want this to be, I just want to check if this is working. Let's generate code. I'd like to do this outside. If we go to generate code, update code, it's going to give you an expression. So let's do that here. Okay, let's turn that down. So now, you know, I want higher, sorry, this is checking the pink ones. Sorry about that. I want, if the value blue is higher than 0.5, it's blue. If it's not, it's the pink ones. So I need to change here too. Okay. So right now our group 1 or this value is way too big. So let's add a channel float threshold, channel float threshold. Okay, and press this little button. So we created a channel float. So right now we can control this value with our slide. So let's change this and this one. So right now the statement is checking the value of this slider. So if we have a value next to 0.8, you can see we have only these particles. So right now we know that these particles that we can see right now have a viscosity of 250, density of 3000, and the boolean is blue is true. In our case is 1. So now let's link our null out base. So how can we use these particles on our dop network? Let's go inside our dop network, our flip object. Let's change some things. I'm going to turn off this wire. Okay. So we have our flip object. Let's turn off this. Maybe we can use our particle field. Check if that works. Yeah, normally I use a source volume to do that. But right now we don't want to emit anything, so let's wire the flip object, change the input type to particle field instead of surface SOP, and let's try and use a pop force. Just check if that is working. Okay, let's see with colors. Pretty cool. And I think I left that turned on. Okay, and because we have on our flip solver on volume motion, our viscosity is enabled and viscosity by attribute, and our density by attribute. Because of that, our flip solver is checking the particles, and if they have that attribute, it's going to use those values we defined earlier. So how can we use that on our pop-up, right? So let's wire this in again, our pop-up to our particle input. Let's go inside our pop-up, and right now we don't want to use our color map anymore. We have our up force. If we check that out now, we are going to see every particle is going up. And as you see, we have only the blue ones going up because of that viscosity, because those particles are pushing the other ones. But we can use, let's go here, let's go use the isBlue parameter, right? isBlue. Remember, this is a float that is 0 or 1, and we can multiply that up force by our isBlue. Okay, by doing that we are deleting these up force we can see on the pink ones, right? So let's go up, let's see these with colors. Now you can see only the particles that are blue are going up. These ones are not having the up force. Pretty cool. And on frame 60, I think we are turning off the force, right? And because they have different densities, some blue particles are going up and they are doing a lot of splash with the pink ones. Let me cache this. I hope my RAM on this computer allows me to see the full animation. Almost there. And let's see the full resolution. Cool, right? One thing I like to do is have this point separation the same as our particle separation on a flip object. This is really important to have the same parameter because the solver is checking the particle separation of flip object. Okay, so let's go here on particle separation, copy parameter, go up on this point from volume, let's place relative reference. Okay, so now our points from volume, our scatter node is using the flip object. Okay, I'm going to pause so I can check, cache this animation. Be right back. Okay, so I have everything cached. And now, as you see, we have particles that are blue are going up. They have different viscosity and different density. It was easy, right? Now you know how to control a fluid simulation using particles forces and mix different fluids. Hope you enjoyed this video. Thank you all for your amazing support and feedback. Don't forget to share your results with us. Have a nice day and see you on the next one.